So what we're going to talk about in a session is innovations in silicon. And most importantly, we're going to talk about not just what we're doing with chips and innovations that we're doing in ASICs, but also the things that we're enabling with those capabilities. Some of the new capabilities that are dependent on the hardware functionality that we build into chips, and show how that progression of innovation works all the way up the stack, all the way from the stuff we're doing in silicon to what we're doing in software to ultimately what we're doing with our products and solutions. So today, anybody who's ever seen me present knows that somewhere in my picture there will be a picture of a rocket or a high-performance aircraft, because A, I'm really into that kind of thing. I really enjoy everything to do with rocketry and aeronautics. And we also put a hashtag on the session called high bitrate, because one of the things you'll notice about Peter and myself is probably two or three things. We tend to talk fairly fast in the session. And the other thing you'll probably notice about Peter and I is we're like an old married couple. We tend to finish each other's sentences and we bicker constantly.
No, we don't.
Well, we don't. We might not in front of the camera, Peter. So starting off, just by way of introduction, my name is Dave Zacks. I'm a distinguished engineer on the enterprise networks team. I primarily work on three things inside of Cisco. I primarily work on what we do with flexible hardware, ASICs, that we're going to talk about today. I deal a lot with network fabrics and things like software-defined access, putting VXLAN fabric in place in the campus, and assurance, basically monitoring and measuring the network and being able to pull telemetry out of the environment to understand how the network is performing. And as you can imagine, all three of those things are quite related to each other, and a lot of them have their basis in what we do and are able to do in silicon. So that's actually where we're going to start discussion today. I'm joined today by my compatriot, Peter Jones. Peter, introduce yourself.
No, you do it.
You want me to introduce you?
Yeah.
Okay, this is power, to be able to introduce Peter. I can say anything I want. So Peter is a distinguished engineer. Peter works on our hardware team. So basically what Peter does is a bunch of things. Peter is instrumental in developing a lot of the ASICs that we're going to talk about today, the UADP ASIC and other silicon that we've developed inside Cisco. He's been intimately tied into that for many years. In terms of development of it, Peter also is a large participant in IEEE and standardization of new forms of Ethernet that we're developing. He led the NBASE-T Alliance as the chair of the NBASE-T Alliance, 2.5 and 5 gig Ethernet, and is currently doing a lot of work in single pair Ethernet. So there's lots of things we could talk about with that. So what we really want to focus on today is innovation, in a word. That's really what we want to be able to talk about, and how the innovation that we're driving all the way up the stack, from the base of silicon all the way up to our product, and kind of connect that together all the way up the stack. This isn't the kind of talk that you normally see a Cisco person give, right? A lot of the things we're doing today are focused on intent-based networking. We're focused on GUIs. We're focused on showing you how easy it is to do all the things. One of the things we want to do is here, because those are all great things, don't get me wrong, but one of the things we want to do is peel back the onion a few layers and show you some of the technology that we're developing underneath that supports our ability to generate all of the things, all the way from innovations that we drive in silicon and software, up to what we're doing with products and solutions. And most importantly, what we want to go through is why these innovations matter. We don't just want to kind of beat our chest and say, hey, we're doing all these cool things, even though we think we are doing a lot of cool things. We really want to talk about why those innovations matter and what kind of new things we're able to deliver to the market because of the innovations that we're driving in silicon. Now, most people have heard of what we're doing here called the network intuitive, this concept of intent-based networking. I'd be amazed if you could go around any event at Cisco and not be exposed at some point to the concept of intuitive networking, intent-based networking. So, a lot of times you'll see that driven through DNA Center. We'll demo a lot of things through DNA Center GUI. That's very cool, this concept of driving intent-based networking. But to me, it's really a stack of technology. That stack starts at the top with things like APIs and the applications that we're able to drive with those APIs, going down to domain controllers, things like Cisco DNA Center, but then ultimately going all the way down the stack. And you see what rests at the bottom of is this concept of ASICs and silicon and custom silicon. So we really want to kind of drill into that and show you some of the latest advances that we've had in this space, right? That the concept of the ASIC, or what we're able to do in silicon, as being the key fundamental underpinning of what we're able to achieve as we move into this area of intuitive networking. So we're going to focus on ASICs for the first part of the discussion. And in my opinion, these are a bit of a hidden gem in our portfolio. We don't talk, in my opinion, about ASICs enough and all the things that we do in custom silicon that are very, very cool. So what we're really talking about here is transistors. at the end of the day. We're talking about transistor, which, as everybody knows, is effectively a digital on-off switch, right? A 1 or a 0, an ability to transmit a voltage or not transmit a voltage, and how many of those transistors we can pack onto a silicon die. If we're developing a silicon die like this, and we're putting a whole bunch of chips, we're manufacturing a whole bunch of chips onto a silicon die, the concept of Moore's law that Gordon Moore promulgated back in 1975, over 40 years ago, basically says that the number of transistors we're going to be able to pack onto a piece of silicon is going to double every 18 to 24 months, right? Most people in technology are very familiar with Moore's law as a concept. That law, quote unquote, has held true for over 40 years and has been responsible for every advancement that we've seen, not just in networking communications, but in digital electronics. Everything ultimately ties back to Moore's law, because that's not a progression of 2, 4, 6, 8. That's a progression of 2, 4, 8, 16, 32, 64, 128. It's an exponential growth curve, and this law has held for a long period of time. So what we see now is the ability to generate and create circuits at very, very small sizes. The first version of the ASIC, for example, that we put into 3850, which I have right here, the UADP ASIC, the very first version of this chip, we produced at a 65 nanometer process node. That means that the wires on here are 65 billionths of a meter wide. Now, since then, we've shrunk this down to 45 nanometer, down to 32 nanometer, down to, in the most current version of the chip, down to 16 nanometer. Now, some of these things can be quite hard to grasp. So let's maybe drill through this a little bit. When we think about that discrete transistor, what we're really talking about is shrinking that down and putting it onto a piece of silicon. This is an awesome acronym. MOSFET. You should go home and quiz your family on this tonight. Metal oxide semiconductor field effect transistor. Effectively, what we're doing with this is taking that discrete tin can transistor, shrinking it down to an element that can be imaged onto a silicon die. So down to about the 22 nanometer process size, we can actually do this with a technology called MOSFET. When we have to shrink it below that, we actually go to a technology called FinFET that Intel invented several years ago. FinFET, we basically spin the transistor on its side, build it up in 3 dimensions so we get greater packing density on the chip, right? So this is most very small chips of ours right now, like the ones we build at the 16 nanometer process node, are built with FinFET. Now what we're actually doing with these is building up gates. Now here's a little known fact. In the technology industry overall, everything that we do in digital technology is only built on 2 fundamental circuit constructs. Not just networking communications, everything we do in every form of computing is built with 2 gates that are called universal gates. Because out of these 2 universal gates, you're able to construct any logic circuit. And those 2 universal gates are the NAND gate and the NOR gate. By combining the NOT AND gate and the NOT OR gate together, you can build any digital circuit. So that's effectively what we're doing as we're building out a chip like this, is constructing millions and millions and millions of these gates together to construct a chip itself. So for example, if we're building out that wafer, building out that die, the first version of the chip that we had for we're going to talk about today, the UADP chip, that went into Catalyst 3850 and 3850 mGig switches, was about 191 million gates. A follow-on version of that that's in the current Catalyst 9000 switches is about 270 million gates that we're packing on there. In terms of transistor count, this is about 3 million transistors, or 3 billion transistors. This is about 7.5 billion transistors that are built onto that chip. Now, when we talk about these type of sizings, these can often be very hard to grasp. What is a nanometer? How small are these things that we're actually building on a chip? So maybe a bit of perspective, a single human hair is about 100,000 nanometers wide. So if you take a look at the hair on your arm or the hair on your head, it's about 100,000 nanometers wide, which starts to give you maybe a flavor of it. But we can do a little bit better than that. If we actually take that human hair, cut it into cross-section, and pretend that that human hair is as tall as the Empire State Building in New York City, then we can get more of a sense of scale. So on this scale, a red blood cell would stretch up to about the 10th floor on this scale with that Empire State Building-sized hair. A bacterium would stretch up to about the 3rd floor on this scale. A single strand of protein here would be about the size of a small dog that would sit down on the sidewalk next to that Empire State Building-sized hair cross-section. And finally, we might come to this little pinprick over here, which is about the size of 3 pennies stacked end to end next to that Empire State Building-sized hair. That's a nanometer. And so we build circuits, we build transistors on these chips, billions of transistors with extreme reliability generated in nanometer sizing. If you don't think that's magic, then I don't know how to explain magic to you, right? And this is what we create when we're building these chips, when we're designing this type of hardware. So just a fun fact, I mentioned at the beginning that I'm a bit of a space buff. I like all sorts of things to do with space. So we put a man here, as long as you actually believe that we put a man on the moon in 1969, 50 years ago. If you don't believe that, we can have a conversation later about why you don't believe we put a man on the moon. But we put a man here using this thing, which is the Apollo guidance computer. This was essential for guiding the spacecraft to land down on the moon. This particular piece of equipment, it consists of about 4,100 integrated circuits, each one of which had one single NOR gate on it, single 3-input NOR gate on it. So in other words, we landed a man on the moon with less than 10,000 transistors, but today we use almost 20 billion transistors in our most sophisticated version as ASIC to route your packets. And of course, that's with all the appropriate TOS and encryption and fragmentation and everything else that we do. All right, so just think how far this technology has come. In 50 years ago this year is when we actually first landed that man on the moon. So why do we develop our own silicon? So for example, when we develop a chip like this UADP chip, this chip took us 5 years to develop, 5 years to develop the first version of this chip. Average in the industry is about 2 years. This chip took us 5 years to develop, and it cost Cisco about $100 billion to build the first one. So it's a major investment of time, a major investment of engineering, a major investment of money to create an ASIC like this. So why do we do that? Why don't we just go out and buy networking chips from some other company? Why do we make our own silicon? And I'd say it really comes down to 4 or 5 key reasons. The first one is what I would call simplified deployment options. If we want to create a deployment, like for example, taking 2 Catalyst 6500 switches, merging them together with virtual switch systems so that they operate as a single integrated entity, we need the ability to extend the backplane header. In other words, a header that transits inside the switch that says, which port did I come in on? Which port am I leaving on? What's my priority when I'm crossing the backplane? We need to be able to extend that backplane header out of the front panel. And if we're extending that out of the front panel, we need silicon support to do that. In the Catalyst 6500, that's done through an ASIC called R2D4 that we built in there. We wanted that simplified deployment option, merge 2 switches and make them operate as one. We need silicon support to make that happen. Maybe we want better insight and optimization. One of the things that I'm going to talk about later is what we're doing with encrypted traffic analytics. And one of the things you're going to see is to enable a function like that, we need to have NetFlow capability on every single packet going through a switch. We need to maintain a full flow information, not just on one packet out of 100 or one packet out of 1,000 with sampled NetFlow. We need it on all packets, right? So we want that. Maybe better security, things like scalable group tags or multiple VRFs or MPLS VPN. The scalability that's appropriate to different places in the network. But the most important part of this overall, I would say, is this concept of flexibility and investment protection through a level of programmability in the chip. So let's explore a little bit what that means. If we take a look at a traditional chip, in fact, how many people have Catalyst 6500s somewhere in the network? 6500s, 6800s, very common. Do people have that? So I'm probably the only person that actually brought a Catalyst 6500 with me today. That is the forwarding ASIC from a Cat6K. It's called Earl8. The code name for this particular chip is called Aludra. So I'll pass that around. You can take a look at that. That's a complete Catalyst 6500, and that's an example of a fixed configuration chip. Cat 6500 is a very capable switch. It does V4 in hardware, V6 in hardware, MPLS in hardware, a bunch of other things, but it has a fixed processing pipeline. It essentially works like this. A packet would come in to the front panel of a switch. We'd run it through a parser block. The job of the parser block is to figure out what is this packet. Is it V4? Is it V6? Is it MPLS? What is it? So that packet comes in. In this case, it's V4. It's a 0800 ether type. So we run it down a set of fixed processing steps within the chip. Layer 2 lookups, layer 3 lookups, maybe some NetFlow. Once we've done whatever the chip can do with it, and we've decided if we're going to forward or drop the packet, in this case we're going to forward it, we modify the packet, we decrement the TTL, we update the MAC address for the next hop, we update some stats and counters, and out it goes. That's how anybody's chip works, right? That's how our fixed chips work, or anybody's fixed chips work. And this is great for processing known protocols. So for example, if you had a 3750 switch, an older 3750 switch in your network, it can do V4 and V6 in hardware. That's great. But present an older switch like that with a fixed configuration chip with a packet that it doesn't know how to process, like maybe an MPLS packet comes along. It's an 8847 ether type. The parser block here at the front of the chip looks at that and goes, what is this MPLS packet? Doesn't know. Doesn't know how to process.
CPU.
So, well, there's only two things you can do at that point. That's absolutely right. We can either dump the packet and throw it away, or we can send it to CPU. But if we send it to CPU, we're going to go from millions of packets per second to maybe a few thousand packets per second. So we typically don't want to do that. So normally we throw the packet out, right? And neither one of those is a particularly good answer, because what we see today is that networks are evolving. If we take a look at how we're building networks today, it's very common that people are starting to take a look at deploying things like SD access. And they're taking a look at putting in a VXLAN fabric in a network. They were going to integrate Lisp. They want to integrate TrustSec because of all the new capabilities that these type of solutions provide. But if you want to do this, you need to be able to route VXLAN, right?
An old dog cannot learn new tricks.
An old dog cannot learn new tricks. That's absolutely true, except we invented a dog that we can teach new tricks again and again and again and again, because we invented a microcode programmable dog, right? Microcode programmable ASIC. That's effectively what we do with the UADP chipset, right? So we can enable functions like this and then make it backwards compatible. So for example, when we came out with SD access last year, we made it backwards compatible onto every 3850 and 3650 switch that we've ever shipped. You could have bought the first 3850 off the line in January 2013 when we introduced it at Cisco Live in London, and you could run SD access on it today. So what we want to do is we want to drive the innovation. We want to produce flexible enough hardware so we can drive the innovation layer into software, but still work at hardware speeds, right? That's effectively what we're trying to achieve with ASICs like this, provide a flexible programmable ASIC that we can update with a new version of microcode, what you would see as a new version of iOS, load a new version of iOS into a switch, reboot it, get a whole new level of functionality, right? That's effectively what we do. So this has been an evolution in our portfolio. 3550 and 3750 were based on fixed configuration chips. These were based on a chip named codenamed Strider 88. This was quite a capable little chip. Did V4 and V6 in hardware, but that was about it, right? Then we came out with 3850, which is the first fully programmable chipset that we introduced into Catalyst product line. And now we've promulgated this chip up and down our product line. So for example, we have the 9200, the 9300, the 9400, the 9500. All of these switches are based on variants of this UADP chipset that is fully programmable, microcode programmable, that we can teach to understand new protocols with a simple software upgrade. So to dive a little bit deeper into that, I'm actually going to hand the baton over to Peter. Peter is going to talk to us a lot about UADP. Then I'll come back and talk about things we do with UADP.
So don't sit down quite yet. So everyone take a breath, because Dave's been going. Are there any questions for Dave before we let him escape?
I can't escape too far, Peter.
You guys are quiet today.
Well, I have one.
Yep.
Jasper, you have a question?
These things are getting smaller and smaller and smaller.
Yep.
And the typical thing that happens is they get hotter and hotter and hotter.
Yes.
So what I see is that, for example, 10 gig switches are much hotter than 1 gig switches, I think.
Yep.
Is there anything in the future you see where we're getting this heat problem like down to having less noisy switches and switches with less moving parts and stuff like this? So there's a challenge, I think.
Yep.
Do you think that is something we have to live with, that we have the noisy switches, or will they get quieter in the future too, because we can do with better cooling or less?
Right. So the first question is about cooling. I'll give my perspective on this, Peter, and then
I'll let you give him the answer.
Yeah. Thank you. So basically, what we're able to do with cooling in chips, all depends on the density that we're driving in a chip, the size of the memory we have the size of the memories that we have in a chip, because that tends to generate a lot of heat. So chips can be quite power intensive. They can have a lot of power that they generate, a lot of power that we need to dissipate. The heat sinks can be quite large. Typically, though, when we're going into fanless devices, we're going into devices that don't require, as much horsepower, because they're typically a smaller form factor, that kind of thing. The heat doesn't tend to be that much of a problem. It's usually more of a problem when we get into the big switches that are handling, multiple 100 gig interfaces and have large TCAMs and that kind of thing. And they typically tend to be in a larger chassis.
Brief.
Okay.
So, Dave's sort of on the mark. So as we go to the smaller dimensions, we tend to get some savings. We also put more stuff in. So if you, for instance, go take a look at the 9400 over in Water Solutions, and you can see it, right? It sucks air down one side. You can tell which way the airflow is going because the first ASIC has a small heatsink. The second one has huge, the third one has a big heat pipe. So it's tricky. So we can steadily put more functions into like a compact switch, but it is always a barrier. So what you end up doing is you do some very interesting engineering to get rid of heat. And if you think about it, if an access point somewhere, see this access point up here? These guys are fundamentally limited thermally because you can dissipate about 30 watts in that thing. So if someone came up and said they want to build an access point that ran at like 25 gigabits a second, you'd probably need to make it this big. So the problem is real. We know about it. It's just a tough problem to solve.
Okay.
Make sense?
Yeah, thanks.
Sit down now.
Okay. Thanks.
So it's very nice to be back again. I see a lot of friendly faces around the table and some new ones. So Dave, it's sort of, Dave steals almost thunder, right? So Dave and I co-present a lot because we work a lot together. So I'm going to try and go through. Now, as you guys know, I like questions. I like explaining things. So ask questions, and I'll try and give you the most accurate thing. And I'm going to try and give you a bunch of the stuff which is the personal experience, because I think that's the most important. So I'm Peter. So the processing pipeline. So I started on this project in mid-2006. And so we shipped in 13. It was a long project. And as Dave said, we sort of started with this structure. And, you know, you build it, L2, L3, L3 actions. We modify along. But then we're going, so what happens if things change? Because at this stage, we sort of realized that just making it faster wasn't that interesting. What we did know was that things were changing. So we changed the parser to be flexible. Now, when I say flexible, it's actually sort of programmable, although you need to be a little nutty to program this thing. So we can control what things we look at. Now, we parse up to like 256 bytes deep, 128 is about what we need. So we can basically add new versions as we go through. The lookups, they're all programmable. So what that means is as a packet flows down the pipeline, we can issue 0, 1, or 2 lookups. The key can be anywhere from 128 to 256 bits wide. And software gets to control what happens. So as happens today, I think our first stage we do layer 2, source and destination, then we do layer 3, then we do multicast. If I need to, I could rearrange that totally. So this gives us the ability to deliver new value to something we've already installed. And I've got to tell you, getting this done in like, this is a common sort of structure for a high-end programmable switch, like maybe an ASR1K. Bringing this down to the 3K, and now like the 9300 case, was a real challenge. And it was, the person who made that decision was brave. So for me, I tend to think about, I want to build, in a car analogy, there's people who want to build Ferraris and Formula Ones. I want to build Camaros and Corollas. So the fact that I could bring this to the mass market, for me, was very satisfying. All right.
Just a quick question. There's stage N, yeah?
Yep.
So what is common at your model? How many stages are common implementations at the moment?
It varies based on the chip. So the original one, I think, was
We're at 15 ingress, 7
stages.
ingress.
Some of the later ones we've added more, we take less. It's just a question of what processing we need. Every stage costs more money. So we trade that off. I mean, building these things is a massive set of compromises. The trick is trying to make the right ones. Statistics are controllable. The scheduling stuff is a little more fixed because that's just hard to do. So, you know, V4 does this. Dave animates his animations with bouncing, so you can see the packet is bouncing all the way down this. You know, they don't actually bounce.
Yes.
They actually flow straight through.
I know, but then it doesn't look as fun.
Okay. So V6, again, dealing with V6 is just a programming issue, as it bounces down the pipeline. MPLS was sort of interesting. I was actually, when we were doing this, I was targeted to write the MPLS application note, which is how we're going to do it. At the time, I believe we actually had to do MPLS really properly, and so that was difficult. And I figured out later on we could actually do it fairly simply. So MPLS, getting it on the platform originally, was mostly a control plane problem, but since we did the IOSXE merge, it became simpler. So I think we ended up adding MPLS in about 3 months worth of development. VXLAN, Dave's mentioned before, VXLAN is the key to the SDA. And what's interesting about this is when that project started, they were actually using Lisp, not VXLAN. We actually converted to be compatible with the data center. Now, the thing about VXLAN is it didn't exist when we wrote the chip. So how do we solve that? So we were thinking GRE, we thought that tunneling was going to be really important. Okay, so Dave's thing is IPv7. I hope they never invent this because IPv6 has taken so long, but I could probably support it. So tunneling gets interesting. We basically have a model where we basically say we'll do a complete pass on both the outer and the inner, because this lets us get a lot of choices. So for instance, when I'm doing an end cap, My first pass just produces the outer end cap. My next pass does the forwarding on it. Okay, so we use the recirculation mostly for things like VXLAN tunneling for GRE. We'd also do it if we're doing something like a crypto block for DTLS.
My question to the rewrites: can you do multiple rewrites, or is it somehow limited?
So it's a limited structure. We can do a lot of rewrites. So, for instance, we can add an entire VXLAN header in one go.
Okay.
And so the actual limitation of the rewrites is a very interesting balance between number of instructions and data accesses, yada, yada, yada.
Okay.
So programming this stuff is not for the faint-hearted. Okay, so 1.0, this is what we launched with. Dave's really picky about transistors. He wants to know exact count. When he asked me earlier on, I said a lot. So this was designed for 1 gig, 10 gig, 24K net flow, stacking, 56 gigabit bandwidth. So the next thing we did was he pulled up this guy. So this became a 1.1, which is the one I've been giving out for a while. So this became really a mass volume, and this is behind. This let us create also the mGig switches and also the fiber switches. So we basically put 2 in a box and made it faster. We added 40 gig, we added MaxSec, 15.8 support. So this was really our second major change, and so this is what we've been shipping in volume. Most of you guys have got some of these, and if you haven't, come see me. I think a while ago we were making, before we swapped the Cat9K, we were making 1 million of these chips a year. So for me, this is massively satisfying because I got to deliver things everyone uses. So we transitioned to UADP 2.0. This is the key to what's in the Cat9K, and this is just an evolution of a family. So this is shared lookups between cores, more net flow, higher speed. So we're just adding more and more. The original UADP 2.0 was really targeted at what became the 9400, and so it supports all the things it needs to do to that switch with the central supervisor. It also exists in the 9300, and it also exists in the lower half of the 9500. So those are the products it sees. More recently, UADP 3.0. As you can see, our naming is very exciting. And I've got to tell you, internally, these were all called Doppler something else. So we had Doppler, then we had Doppler CR for cost reduction, Doppler CSR, Doppler D, Doppler E, and Doppler G. So we're not very inventive. And by the way, we will give you these slides later on so you can look. 20 billion transistors, 16 nanometer. This one took us a while. So the customizable ASIC templates, this basically means we can choose how to allocate memories. The tables are double width. So traditionally with forwarding ASICs, you only have half the capacity for V6 because we put into V4 entries. In this particular one, we support V6 natively. 1.6 terabits of bandwidth, which is sort of a lot of buffer. So this was built to be core and distribution switch. Oh, so back up. And this was built again, so we added in 25 and 40, and yes, Ivan.
When you say that IPv6 takes twice as much space as IPv4, that means you're only doing lookups down to /64s, right?
No. So when we do our full lookups in all the previous generations, so we're doing a full lookup for the IPv4 address. Mm-hmm. When we did IPv6, we would consume 2 entries.
Yeah, but that's 64 bits.
No. Okay, so figure it out, right? So how long is an IPv6 address? So we have 128.
It's 128, yeah. And the other one is 32.
Address compression.
No, we don't do address compression. So the structure of our lookups and everything else was we could fit one v4 with some extra stuff. We're not just looking up the address because we're also looking up everything else that goes with it.
Okay.
Key point. Mm-hmm. In general, previously, for a V6, you got half the capacity of V4, not in this case. Mm-hmm. And thank you for catching me on this. So the other thing I want to point out is down here, we added in the 25 and 100 gig. So other things I can talk about is that we have a speed progression happening. What used to be 1 gig, 10 gig, 40 gig is becoming 2.5, 25 and 100. And so this is where we really came to that 25 gigabit per lane. Yes, sir.
So it seems that more features, more capabilities coming with this chip, is it?
Correct.
Plus speed as well. So you position it in the core network.
Distribution and core, yes.
Distribution and core, especially in the core, okay, I may need speed, but not feature, like VXLAN. Many other features.
Sort of different things. I mean, part of this is, we've had that argument, right? Do you build a core that's really fast and dumb? So what you might also see, this might, for instance, end up in a distribution layer with maybe a 9200 beneath. And so we have to address both those. So I understand, if you're building a really dumb fast switch, that has some use cases, but we also have the other ones. So, I mean, this might also go in. Maybe we're in a person who's doing a replacement of distribution switch but has got Catalyst 2K. So those cases exist.
Yeah, there's also the other problem. The customer who doesn't want to listen and puts the switch in the wrong place, and then you have a problem.
Yes. Strangely enough, you can't go and tell customers they're wrong. You can advise them, but okay, core architecture. Network interfaces on the edge. Packets come in, they go through an ingress FIFO. You notice we've got MACsec in here, which is a line rate MACsec block. So these days it's either 120 or 256 because we believe in crypto. Packet goes in the packet buffer. A copy of it goes into the ingress forwarding controller. We shared lookup tables in the middle. Then basically the packet comes out. What comes out of the edge of this ingress forwarding controller is basically the decision. So the packet was sitting and waiting in the PBC, was waiting for a decision. Once I get it out, I decide whether to queue it or chuck it. We use a stack interface. Even with systems that don't have an external stack, we use the stack internally to connect systems together. So fundamentally, we've built a distributed forwarding system.
So you don't build the leaf and spine fabric internally like in data center switches. No. You have the bus.
So the fundamental architecture we have is a distributed forwarding system with a ring. Yeah. That's what we have. And so we've adapted this to other places. Egress forwarding controller. So egress forwarding controller is where we do our rewrites. And we do things like egress polices, egress net flow over there. So it has about half the pipeline length of ingress. Rewrite engine is sitting out here. Egress FIFO goes out to the ports, MACsec again. This is also where the recirculation path goes. So hold on a second. And so one of the things is, for us, the recirculation path just looks like another port. Yes, Ivan?
As you use the ring in the back, you are probably exposed to something like the NUMA architecture issues, that going from here to here is fast, but going from here to there is really slow because it has to traverse like 2 other nodes.
So the answer is no.
Okay, that's nice.
There's a whole long story about stacking. We actually do multiple paths. We do segmentation, reassembly of distributed credit control and spatial reuse. So the answer is no, we don't have a problem with that. Our transition on the way through the stack is very fast, so we treat that as high priority. So we don't have the requeuing problem.
Okay.
What about between the ingress and egress? Yep. Is there a speed difference? So do I have maybe head offline blocking issue?
So in these, our general principle is these things run line rate. So in the later chips, we've actually adjusted, we're line rated around about 200 bytes. So early on, we were line rated any speed. So they're the same speed. These guys actually run the same clock.
When you are within one ASIC, what if you have to traverse the stack interface?
So the stack interface comes at varying speeds. The original one was 240. Later ones are just getting faster. Yes, it's possible to block on the stack interface.
Thank you.
But we have full queuing and scheduling towards the stack. So we have a full scheduler, distributed credit control, so we get a pretty good performance. At some cases, we'll build a non-blocking. It just really depends on the combinations. In general, if you push up the ports, you'll eventually block, but we have a very elegant way of dealing with it.
So it could be stack interface or through the switch fabric?
We don't have a separate switch fabric, right? For us, the switch fabric effectively is the stack interface. We don't put in a switch fabric chip.
I was wondering, how about the multicast? Is that still the same?
Multicast is a beautiful thing because I put the packet on the stack once. I then replicate it. So everyone who needs a copy grabs it off.
Yeah.
What I then do is I replicate per port 1 copy, and then potentially per port I replicate at the front multiple copies. Right. So replicating across the ports is like a layer 2. Then if it's different VLANs, it's inside. We're a great multicast engine.
Can you just quickly touch on packet mirroring? Is the same procedure if I want to mirror a port?
Yes, it's just a multicast. So
Okay.
yes, so if we're doing like a span thing, we can select the 8 span sessions. We have a whole lot of ways to select that. Yes, so for us, packet mirroring is just a copy.
Just for me to understand, sometimes I have limitation. This switch can do this 5 ports of packet span and so on. The limitation is coming from your pipeline, or where is this coming?
The limitation of 8 span sessions?
Yeah.
It gets nasty because we have a whole lot of reasons, so we actually carry an 8-bit bitmap.
Okay.
Now, that's 8 span sessions, but I can have lots of different filters putting into them. So let's have a longer conversation later on, because it gets different. ER span is a little bit different again. So with a basic span session, I can have 8 span sessions that they can put out to a whole lot of ports. So a span session doesn't have to be only 1 port.
Okay.
Okay. So it's basically there's a policy filter on the way in and there's an expansion on the way out. Okay. Progress stages, I'm going to run through this really fast. The basic idea here is I start off with a parser. I go through the pipeline, the order of things I do, tunnel lookups, etc. We rearrange this on a regular basis. Balancing it is really interesting. I get the choice of what happens when.
So there's 256 bytes right there,
Yes.
which covers some of the IPv6 extensions headers, but not all the stupidities they throw at you, right?
So yes, so for instance, there was Geneve, which is really huge. So for those cases,
Oh, segment routing.
SRv6.
so we are built for what we need, and so if we can't parse anymore, so we'll get some number of layers, right? If there's more beyond that, either we made a decision or not. If we can't, I can recirculate it and do some more. We don't tend to do that, so I could strip off a tunnel. Yes, sir.
Can you do Geneve then? Because IETF is pushing
So
that.
I looked at Geneva a long time ago, and what I sort of thought was it's not suitable for us because they put so much stuff on, and so Geneva is a DC problem, not my problem. So we looked at it in terms of, could we do this? But I think the way that was constructed wasn't designed to help us. Bunch of lookup tables in the middle. Right here, millions of times a second. So we share this across cores. We actually have cores and sublayers. All these lookup tables are shared. So we actually program the parsers the same on each way. As I said, we tend to do all of our forwarding stuff in the middle. We do egress filtering, egress rewrites. Right, 9200. So I told you guys I started working on this stuff in 2006. We planned to take over the world. We've eventually got there. So the 9200 is the newest form. It runs what's called UADP 2 Mini. And we do have some of these for questions, possibly. So from my point of view, this is like a completion because we always want to do 3K and 2K. So now we're now rolling out the value proposition. We rolled out in 3850 and 9300, we're rolling out to the 2K class. So who's got 2Ks today? No one there? None of you guys have got Catalyst 2K? We sell an awful lot of them. What this means is we're able to offer that investment protection, flexibility, and the ability to evolve the network to the vast bulk of our customers. It's like we've taken the very cool feature from the Camry and we've made it available in the Corolla. So for me, this is like, it's one of the really proud moments. Question? No? All right, it's the flexible ASIC. What else we got? We've got resiliency. MaxTech is 128. Programmability, we've got that over through Yang. SD access is sitting out there as an edge node. And just as a fun bit, because we're building a low-end product, we actually wrap the CPU into this. So this is both the forwarding plane and the CPU. And that's a decision because this is the volume part.
So you build your own CPUs, or you just merge together your die with someone else's die?
So that's getting a little bit interesting in the depth. So I don't really want to go down that path, but it's not a multi-chip module.
Okay.
So yes, we integrated it. Stacking comes either, there's two sorts. There's a more modular, less modular. The stacking is either 80 gigabits or 160 gigabits. We're really trying to take the value of like 9300 and downsize it for the people who need it. Right. It's just like the original UADPs, but down a little slower, right? 100 gig of bandwidth, some NetFlow 16K. We believe in NetFlow. Stacking capacity, 14 and TCAMs. And so some of these numbers are compared to the original 2K. It's basically bringing the 3850, 9300 experience down to the 2K level. That being said, I'm going to hand over questions before I go.
I have one question.
Dominic.
Just in general, so the design is going to a single ASIC design in most cases here, yeah? So,
So clarification. We have a family of ASICs with a common architecture.
yeah, sure, but for one device, yeah? So do you think that in the future we will see, I don't know, special chips for something, or all will be integrated always for one device and one chip, more or less?
So
You are doing MaxTech, for example, on the chip. It's not an extra encryption chip, yeah?
So we pull as much as we can in because that's where the value is. So we tend to push. So some things like fire devices we push out. We want the logic that matters in our chips. So we pull in as much as we can. But if you look at like 9400, there's 3 of them. So it's not a single chip per device.
Okay.
But we try and have the core function in our ASIC. Right, so there are some people who will tend to use, they'll have a basic forwarding silicon, they'll have something on the outside to do extra things. We pull all that stuff in.
Yeah, so more or less I can understand if I want more ports, I just add more ASICs, makes sense, yeah. I'm looking for features that you cannot integrate where you say, okay, this always needs to have an extra chip, yeah?
So the way that we deal with that today is what we're doing mostly is we're now wiring, we wire a 10 gig port up to an Intel CPU. So if I had to, I'd push stuff up there and use some of the Intel software forwarding. We could do that, but what we need to do is we need to make sure that basic things everyone runs, run in hardware. That's our goal.
Okay.
But no, we don't tend to put external like crypto chips on. It just gets tricky, it's costing the board, and so it doesn't work for us.
It's old school, yeah.
Depending on what you're building, right? If you're building like a high-end software forwarding thing, maybe it makes sense. I mean, if you go and look at building software forwarding with an Intel device, they have crypto offloads. So a lot of people used to use like a cadmium nitride for a crypto offload, and you have to do very complex stuff, that might make sense. We do MaxSec, we do DTLS, we have other cryptos coming, but we don't tend to do some of the obscure things. That's a problem for a router or something else, or a firewall. Does that make sense?
Absolutely.
Now that you said that you have CPU on your die, I'm guessing it's ARM, right?
Yeah.
Okay, thank you.
So there's a few you can do. ARM is the easiest to integrate.
Yep. ARM Cortex.
Packet forwarding, is that the entire frame that gets forwarding throughout the stages, or is it broken into like high-end routers into cells?
Okay, so let me try and answer the question. So when the packet comes in the ingress forwarding controller, what actually happens is a copy goes in the packet buffer, the whole thing goes in the front of the ingress forwarding controller. We then do our parsing and we throw it away. So then when we actually forward it, when it goes in the packet buffer memory, it's in the 256 byte cells. They then get queued up and they go across the stack in that size. So our native internal size is 56 bytes.
I think his question was more when the packet's going down a processing pipeline, what do we do with the packet descriptor going down a processing?
Okay, so on the way down this, so we have this enormous thing called the packet state vector, which is both the parsed header fields and everything we find. And it's an enormous thing that basically flows through the pipeline. And we just accumulate data on the way through. We get to this thing called IGR at the end, or EGR. This is the magic happens here. Because a whole lot of times we can't make a final decision on the way through, so this guy arbitrates. So for instance, I might have a case where I have both an L2 and L3 forwarding result, because I find a security ACL has done a deny route. So I don't know until I figure that out which one's going to win. So there's basically a massive descriptor that rolls through this thing, where we carry the parsed header fields, look up results, all this other stuff. So the packet itself actually dies here on this path. All we just do is we carry all the fields through, and this guy produces a result. And then we carry this big descriptor goes on the front. The big descriptor gets put on the front of the packet and it gets hauled around the system.